So, well, as you can see in the program, we've been looking at all the round 2 candidates. And as you all know, these were much more mature, so we were very, very happy to start with these. They all look very solid. And so in the first round, we did a staggered approach of first doing cryptanalysis, followed then, if the system survived, by an analysis of the proof and analysis of speed impact. Whereas in the second round now, we proceeded with all 3 of these at the same time. So we had a much bigger team in Eindhoven, and we also joined forces with Daniel J. Bernstein from UIC. And thanks to this bigger team, we could also afford to do all these 3 things in parallel. Dan sent a lot of emails on the KpqC mailing list regarding the implementation and benchmarking issues. And we were happy to see that many of you updated the submissions. And we did our share in re-benchmarking, updating the benchmarks. Several of the systems are now included in SUPERCOP, so they are being benchmarked continuously also on a variety of systems. We are seeing still changes coming in. We're trying to keep up, but the last few days have been somewhat challenging in that respect. When we had issues about proofs, we only emailed the team because these were kind of small things where we wanted to offer our assistance rather than going like, hey, you have a big issue there. Of course, if we found an attack, we emailed the KpqC mailing list also and typically inform the designers first. Okay, I will now go through all the results we have, starting with chems and then moving over to signatures. So I have one slide with the highlights for each of the system. So for, oops, and I realized now that I think about it, I forgot to put one line on one of the slides. All right, so for the chems, I'm going alphabetical order. There's no ranking or anything implied by that. So Entro Plus is the first system we looked at for the first of the system I'm presenting now. It is a lattice-based chem, and the system is very close in the design to NTTRU. So you see the NTT, like the number theoretic transform in there, and NTTRU introduced one cyclotomic polynomial, which is a trinomial, has a degree 2 to some power, 3 to some power. And then in Entro Plus, the designers generalized this to several of these, achieving a better scaling and so having system parameters for all 3 considered security levels. This is not as much as Entro could be scaling, but it's a lot more than just pure power of 2 cyclotomics, or even what you would be getting with the Dalton Kybers or with the module lattices. Another interesting feature of Entro Plus is that it avoids re-encryption. By having, well, first of all, Entro, you can recover the randomness, and then designers did a kind of feedback loop so that the message they want to encrypt defines the randomness. The randomness can be recovered, and then they're using this randomness in order to also modify the message. So eventually, it's M that's being encrypted, R that's being recovered from the message, from the decryption, and then by that they can check whether the message is valid. Now, in the first round, there was an issue in this SOTP transform, which gave them a CCA2 attack, well, distinguishability attack, because there were 2 messages, or you could modify the ciphertext a little bit so it would look different and still decrypt to the same message in, well, 1 out of 4 cases, but because this was for each and every of the coordinates, this helped. Now, in the second round, the designers changed this transform, and from what we can see, there is no more corner case. On the proof of security side, we're a little bit concerned because it changed the definition of rigidity. So rigidity is this feature of, can you go back uniquely? Are there any ciphertexts that would decrypt that are not valid encryptions of plain texts? But we tried and we didn't manage to get up any hooks in there. So we think it's probably okay. And then on the round 2 software, Dan was very happy that it was easy to integrate into SUPERCOP. So this has been in the benchmarking since, I believe, July. So it's been one of the first systems to be integrated. And the Entro team was also responsive. The Entro Plus team was also responsive when there was a correctness issue. Okay, So then the next one is Paloma. So that's a code-based chem using Gopher codes. Now we know quite a few Gopher codes versions of this. So this one is using Gopher codes where the Gopher polynomial is not necessarily irreducible. In fact, it is absolutely not irreducible because it splits completely. So it is using a generalization that is fine for the definition of Gopher codes or also the McLeese system, because all we need is that the polynomial is separable, so it doesn't have repeated roots. And then with their system, they need a generalized Patterson decoder because the normal Patterson decoder works only for irreducible polynomials. Now, this Patterson decoder comes from a different paper and so the designers adapted this to their special case of having a completely split polynomial and inherited some quirks from this generalized Patterson decoder, in particular that it had some interesting features of how to handle zero in the support set. We managed to do some reaction attacks, first on the software error and then also on this Patterson decoder, returning all zeros. My July talk was about that, so I'm not going to spend more time on this. The designers in early September, late August fixed their system. In the submission, they changed the proof, they changed the system to insist that the error vector returned at the end has weight exactly t, so that if there's something of weight less than t, it would be caught by the implicit rejection. And from all we can see, that fixes the issues we encountered. And then just 2 days ago, there was a new software which is also then implementing this. I have not had the time to look through the software update, whether it captures all of this, but I do believe that, well, I understand how to do this test, and it should be fine in the software. But there were lots of other things that we identified. There were some issues regarding constant timeless, etc. And both in the sampling, but also in the multiplication and other routines. And I've seen the changelog to the software that the designers have addressed those. But again, 2 days while having some other things were not quite enough to look for those. Yeah, in general, happy with Paloma. You know that I like the classic McLeese system, and Paloma is sufficiently different, but I can't see a weakness in the different choices. Redoc, in the first round, we did a few attacks on this, but we also saw that one can fix it. And then the designers did some changes, including changes we suggested. On the other hand, they also ended up with somewhat smaller parameters overall. I haven't traced through whether the same attack would also work on our parameters, but Alex Pellegrini and Mark Fostermans were able to mount a new attack, which they termed the Pad Thai attack, because Alex was in Thailand at that time, and there's a lot of padding going on. And the interesting thing about this is that it really uses the rank metric codes having a very small rank weight on the second component. And a small rank weight means that, well, say if the rank weight is at most 2, that means you're having only four possible elements. You have the 0, you have the first basis element, the second basis element, and the sum of those two. And if you have rank weight 3, then you're going up to, well, 8 in total. And these are very few elements. And the error positions are randomly sampled from those 4 or 8 positions. And what the attack is doing is it's brute forces through all possible arrangements, so all possible ways that those 4 or 8 elements can appear in the vector. The vector has length n minus k, so they have a cost of 2 to the t2, which is, well, this number there, and times n minus k. But the n and k are chosen relatively small. You can see the parameter table below, so n is 30k is 6 for the smallest and 58 and 10. So we're looking at most 2 to the 40 times, well, then a t3. So that's where the main attack cost comes from. And then for each of those, they have to do a linear algebra attack, where they assume that it's the right arrangement, and then continue. If it was the right arrangement, this attack would succeed. If it is not, then it fails. And so the overall costs you can see in the table below of this attack are significantly lower than the security level they were designed for. It's not impossible to pump it up again, but at the moment it doesn't meet the security levels. So there are still some little bits of improvement. So this analysis doesn't capture all the improvements we could do. For instance, in this arrangement, whether it's this of the 4 vector or this of the 4 vectors in the same position, it is sort of the same arrangement. The 0 space plays a special role, but among the other 3, any permutation of those would give the same. So in the end, instead of having to run through 2 to the T2 and minus K, we actually get a reduction in this factor, which matters in particular for the 256-bit security level, where T2 is 3, and so we get a bigger boost there. On the software side, we didn't see any function C implementation, but we did a Python implementation. I mean, the system works as described, but we were a little bit surprised that we didn't get anything to evaluate on the implementation. So we don't have performance figures for that. On the other hand, given that we managed to break it again, it might also matter less. And sorry for the typos, I'm seeing an extra I there. I'm sure I fixed this one and also the other one, so I must have messed up in transferring the right PDF file. So I hope that there's no more issues later on. Okay, so then the last game is SMAUG-T, and that is the merger from SMAUG and Tiger from the first round. SMAUG-T, both by name and also by the parameter sets, is mostly SMAUG, but there is a timer variant of SMAUG-T which does capture the small ciphertext sizes of Tiger. So Tiger was much more aggressive in shortening the ciphertext using error correction. Most of SMAUG is not doing error correction, so the timer variant is quite different. It's only for the 128-bit security level. And so it is, if you want a small cipher and, well, really care about small ciphertexts, then SMAUG-T is, the timer variant is the best one. Otherwise, it is still an interesting alternative to Kyber because it achieves smaller ciphertext. And we were happy with the proof, so we had some very minor comments. Now, in the on the software side, you have seen the emails regarding correctness issues, and there were some timing leaks that we showed could be exploitable. So there was a Fisher-Yates sampling, and but we have also seen quite a few recent software example updates. So first the main SMAUG parameters, and then more recently the timer variant. Okay, this is it on the CAMs. I'll now move on to the signature systems and briefly checking for the time. Okay, so on the signature side, again in alphabetical order. So we looked at AIMER. So AIMER is the one MPC they had based system that is in the KpqC competition. It's also in the NIST competition, and there are many more based on this design paradigm. What distinguishes AIMER is that it uses the symmetric primitive called AIM, well, designed by the AIMER designers. And this AIM is a very simple, very performant construction. It has a small compact design where you're taking the ciphertext, computing some modular exponentiation of it, and then doing some operations like XOR on those to hide this algebraic structure. However, there is still a lot of algebraic structure on this, and that led to several attacks in the first round of AIM, well, of AIMER, but all of these attacks were targeting the AIM symmetric function. In general, the proof follows a known framework. There were some small issues, but they have all been fixed. There were some things where we're not fully happy with the explanation given. So in the second round, the designers changed several of the parameters, changed how these exponentiations work. The concern was, I mean, the reason that the attacks worked in the first round was that the exponents were very small. So you could mount an algebraic attack where you use this small exponent to have a low degree for numbers. Now in the second round, the degrees increased, and then there is a use of an inverse function. Now, if you're using an inverse in a fine field, you're getting a very large degree relatively for free because, well, for the verification part of these implicit in the head steps, well, the inverse is just can be replaced by a modification, but the algebraic degree gives up. On the other hand, you can often also trace the algebraic degree through this inverse. And so we felt like there is still a lot of algebraic structure that can be exploited. Myron Mazoun was looking into this in the first round, and he's also looking at this still. So we hope to have a little bit more of an announcement coming up. Nothing fully devastating, but well, there is a structure in there, and depending on how you count the cost operations, you're getting something around or slightly lower than the estimates. So in the software, there were some correctness issues, but in general, this has been fixed and is there. So there were some timing variants, but the AVX implementation, so the more performance software, doesn't have these timing variations. It's only in the reference software. For HETI, this is a system which is using module lattices. So it's like the lithium, but shows us what one can do with 7 extra years of research. So it's getting better parameters than the lithium, but better parameters in the sense of smaller signatures. And well, as you can see from the NIST competition, choosing the lithium and Falcon, the size of the signatures is a serious concern about it. And so HETI has a nice performance point there in being smaller. This comes at a bit of a performance loss in speed, but typically the size matters more than the speed. And in the round 1, we identified some issues, and there was also the general security issue in the lithium, which the designers had already addressed in round 1. But if you only count the official submissions, then the round 2 fixes those. There were some parameter choices where there was a K2, which wasn't quite in the right range, but that has been fixed by now. And then in the timing variants, it looked like it was rejection sampling. So those we marked as could be released, so it's fine. And there was one division which, at least for Kyber, was a problem, and then designers just removed the division, replaced the division by its other codes. Pretty happy with the software. It's also in SUPERCOP, and I should also say HETI is also in this competition. MQSign. So MQSign in the first round got a bit of a bashing. So they had variants. So it's in general a UOV, unbalanced all vinegar design, multivariates. And they had tried to design something with sparse variants. So they had sparseness on the oil or sparseness on the vinegar part, and they had the normal. So R is the regular version and S was the sparse version. All of the versions that included some sparseness had a security issue in the first round, and so they were promptly removed in the second round. And then the RR version stayed, and then it introduced a new version called the LR version, which removed the sparseness because it was a real attack target, but then changed, well, there was also a circulant structure on the matrices. And the circulant structure gives you sort of a hint that certain arrangements of vectors are more likely to work. And so with this, well, not quite brute forcing, but looking through the structure, Monika Tomoshka found a way of how she could sign 0 without a private key. So 0 is then the output, would be the output of the hash function. It's not that we can sign the message 0, but you can get a valid signature on 0 in the LR variant. We have not found anything on the RR version. On the proofs, well, there is a reference to another paper. Approval security people would prefer to see the system using the full domain hash. Now that would increase the size of the signature by 32 bytes, but we still think this is a worthwhile trade-off to make the approval security people happy and, well, benefits there. On the software side, there were some timing leaks, some software issues, but it's also on the positive side, we'll see more of this from Dead Runcie in a moment, that it is a very efficient system. And then finally, NCC Sign. NCC Sign is another lattice-based scheme, this time using ring learning with errors. So not the module structure, but otherwise it is very close to how dilithium is working. And also for the security proof, it is referring to, well, heavily referring to what dilithium is doing. Sorry for the noise on my end. So much so that the proof is sort of saying, well, look at the dilithium proof, and then you can get, yep, I realize there is some problem right now. Sorry for that. I was trying to covertly change something in the back, and that didn't quite work. Sorry for that. So the NCC sign is using NTTRU polynomials and the entroprime polynomial. Actually, yeah, this is the old set of slides. Sorry. The NTTRU, as I said, also in the Entroplas version, is using a cyclotomic trinomial. And this is what they're also using for their speed. So if it's faster, it can use the NTT. On the other hand, if one is concerned regarding structure of these lattices, then NCC sign keeps that structure. So there is some issue in the security proof where some pieces are missing. So there's a start of some theorems or some lemmas where then the second part wasn't there. We believe it's all fixable, but notice that there was, well, a little bit missing. On the software, yeah, as I said, it's only the trinomial case, some small correctness issues, and then, yeah, Fisher-Yates sampling gives you timing issues.
All right, so let's see. Hopefully people can see the new slides. Okay. All right, so what these benchmarking slides will show is some results from the SUPERCOP benchmarking and testing framework. These include 6 of the KpqC submissions. So Entry Plus, this includes the latest Entry Plus software. For SMOG, this does not include timer, but it does include SMOG T1, T3, and T5, where software was recently announced. For Paloma, things are not included currently. That'll happen soon. Of course, you should watch the webpage bench.cr.yp.to for things that get added later. Along with the graphs, including these 6 submissions, there are some selected baselines, for example, elliptic curve cryptography and a few post-quantum systems. So you can see how these compare to those. Now, I should give you some warnings about these systems. The graphs that I'll show you are for 2 selected CPUs. One of them is Intel Haswell, which was also for the old NIST competition designated as a comparison platform. And the other is for AMD Zen 3 CPUs, which were introduced in 2020. There are, of course, many more generations of Intel CPUs, AMD CPUs, ARM CPUs, 32-bit and 64-bit. Other platforms, Intel, AMD, and ARM are the most popular, but maybe in the future people care about performance on RISC-V, for example. And then you can have different performance depending on the CPU, so that the graphs I'll show you are for these 2 CPUs. Another warning is that the timings that I'll show you are median timings. They do not show any of the variance from one run to another. They are, so everything was measured many times, and then the median timing is what's reported on the graphs. If you have something which takes a variable amount of time, then, well, that creates some statistical errors in the median calculation, and sometimes it means it's faster, sometimes it's slower. That makes comparisons more difficult. Another warning is that the speeds that you're seeing, it's the speeds of the software currently in SUPERCOP, which is not necessarily the best possible. If you have a new system, then typically things get faster as people put more work into it. And the speed up depends on the system, and it can be difficult to predict how much faster things get. You should not expect that just the first implementation is going to produce the optimal code, because, well, compilers do a very bad job of optimizing software. Another warning is that if you look at the total cost of your application, then that is not necessarily positively correlated with the cost of your cryptographic computation, because the total cost is, well, your cryptographic computations plus the communication of your cryptographic object which can be more expensive than the computations you're doing, plus other costs in your application, which can be much more than the cryptography. So depending on your application, depending on how much communication you have versus computation, you might have something being faster if you just measure the speed of key generation, for example, but slower for something which is not the best choice for your application. So sometimes applications are doing so much computation other than cryptography that you don't actually notice the cryptography at all. And then, well, all the cost measurements for the cryptography really don't matter for those applications. If you want more CPUs, then look at the website bench.sierra.yp.to. Also, there are tables which show quartiles. And this is a continually updated site, which has had many years of updates, and that'll continue in the future. And so you can see if people have faster code, then that will show, assuming it's submitted to the benchmarking project. Okay, let me start with signatures. So I'll go in alphabetical order through submissions, where signatures are first. And then this first graph and the second graph, these are for, you see the dots are the same positions here, just the labels are sort of chosen by one of these random physics simulations processes. So these dots are for Intel processor and an AMD processor just measuring sizes on both axes. So of course the processor doesn't matter for the sizes, it's the same size just depending on the system. And what you see is in the top left, you see some dots for AIMER. Now, what does top left mean? Well, the horizontal axis here is the space for your public key. And the vertical axis is the space for your signature. And so that means if you have, well, the public key being small and the signature being large, then that's the top left. In the bottom right, you see MQ sign. Now, you also see there's some T colons, there's a comma T colon. This means MQ sign has a T colon version and a non-T colon version. And what does that T mean? It means that there's an implementation which is not declared to be constant time. And in the case of MQ sign, there are two implementations, one of which is not in fact constant time and one of which is constant time. Of course, this doesn't matter for the sizes, so both of those have the same dots. Also, you see that the MQ sign LR versus RR have the same sizes in this picture. So there's really only 3 dots for the 3 security levels for MQ sign. And that, again, to the, so top left was when you had a small public key and big signatures. Bottom right is when you have a big public key and small signatures, which is typical for multivariate quadratic systems. And then in the middle with, well, not the smallest public keys, not the smallest ciphertext, but also not the largest, you see various lattice-based systems. So you see Falcon, for example, as a baseline for comparison, dilithium as another baseline for comparison, and also there's one Sphinx example in the top left that you see as another baseline. And then you also see, well, Heyte is somewhere, I mean, comparing the sizes to Falcon, it's not quite as small, especially in the signature size. But if you compare Heyte to dilithium, then you see that at each security level, it's significantly smaller than dilithium. And then NCC sign, you see, is also in this clump, a bit more sort of up compared to Heyte. So NCC sign 5, for example, is along the diagonal from like the y equals x sort of diagonal. Well, okay, it's not y equals x. You can see the labeling is it's log scale in both axes, so you see every line is doubling. And then, but along the line that's sort of visually y equals x, you see NCC sign 5 has sizes a bit bigger than dilithium 5. Okay, so that's how Heyte and NCC sign compare in the scatter plot to dilithium, which is a plot of sizes. You also see in the bottom left, there's some elliptic curve systems. Ed 25519, so that one has, well, 32-byte public keys, 64-byte signatures. Ed 448 Goldilocks, you see a T there because that software is not declared to be constant time. Some of the software in SUPERCOP was submitted before the constant time feature was added, this tracing of constant time implementations. And so it's not always marked. Maybe it is constant time, maybe it's not, but it's not marked. Okay, that was sizes. Now, of course, this does not need a big benchmarking framework to just plot the sizes, but this graph is actually showing some performance numbers, including, well, sizes versus timings. And then this, what you see here is, let me give the qualitative comparison. In this graph, you see that, well, MQ sign up sort of top to the right, well, it's not necessarily the farthest thing to the right, but anyway, this is saying that MQ sign, the key generation takes a while. And then this is quantified. Again, these timings for the horizontal axis, this is something which maybe can be improved by some amount depending on which system. We have done some analysis of the performance of each system, like how much improvement is possible, and it varies from one system to another. And then in some cases, it's actually not obvious how much improvement is possible because there's, for example, binary field arithmetic in MQ sign, which is something that can be done in many different ways. And you see in more the bottom left, well, the very bottom there, you see Aimer has fast key generation and small public keys. In the sort of middle, you see the lattice systems, NCC sign, and dilithium and Heyte. And Heyte is a little slower for the key generation. So it's a little on the right of the lattice clump there. You also see Falcon has significantly slower key generation, even though the sizes are good for Falcon. That's an example of the baseline. The existing signature systems have these trade-offs. You also see Sphinx with some pretty slow key generation, but small public key. And then, okay, this is something which these two graphs, now you see the dots moving a bit. This is the old Intel, 2013 Intel versus 2020 AMD. The dots are moving, and maybe I'll skip the going through the exact changes here. All right, another of these speed graphs, of course, you take time to sign a message and time to verify a message. And now this, comparing that to the signature size, you get a graph that looks very different. So here you see MQ sign is close to the bottom left, almost as good as an elliptic curve system. And that's something where the signature size is small and the signing is fast. And when you use a key again and again, you don't have to worry about transmitting the key. On the other hand, if you're using a key a small number of times, then just looking at the signature size is not maybe what you want. And then the lattice systems, you see, well, different possibilities moving up in the graph. You can see Heyte is again somewhat slower than dilithium, for example. NCC sign is more competitive in speed with dilithium, although a little bit bigger. Heyte is a little bit smaller. And then you see farther up to the right, Aimer has slower signing than the lattice system. All right, and then similarly, this has, well, you see dots moving a little bit as I flip back and forth between the older Intel processor, the newer AMD processor. It doesn't drastically change the graph, but if you do very close comparisons, then you can see that there's some differences. Okay, then finally, there's some graphs where we're looking at the signatures versus the signature space versus the verification time. And here you see, again, different kind of picture. So MQ sign, actually, sorry, I realize there's multiple graphs here. So this one, yeah, so sorry, this one is the signatures versus the signature space versus the verification time. Then this one was the key size versus the signature time, which is why MQ sign jumps way up to large sizes of a megabyte or so. Okay, and so you can see looking at these scatter plots, we'll put these online, and then you can see looking at these scatter plots what the comparison is between the different systems. For instance, in this one, Aimer is very small, so it's far down in this graph, but well, the timings are not as good as some other systems. Heyte is reasonable timings, NCC sign reasonable timings, and you can look more closely and see how those compare to dilithium. MQ sign, well, the key sizes are big, but also the timings are reasonable there. So it's far up, but it's competitive in terms of in terms of the speed. All right, and then I should show you some chem graphs, and here similarly, well, you can look at these scatter plots for sizes, and you see that there's sort of a diagonal line of lattice systems. And then also for comparison, there's McLeese in the bottom right, and that's where the key is big and the ciphertexts are small. Paloma has similar characteristics to that. And then also for comparison, this graph has SMOG and Entru plus. It also, for comparison, has some other Entru variants and has Kyber. And you can see SMOG is a little smaller than Kyber. Entru plus is maybe a little bigger than Kyber. Entru plus, if you look at the speed graphs, then you see that Entru plus is faster than Kyber, although this maybe depends on Kyber 90s versus non-90s. This one is key generation. And here you can see Entru plus 864, for example, is competitive with Kyber 768 in key generation time, although a little bit slower, little bit bigger, but pretty close. Entru plus 1152 is a little faster than Kyber 1024, and well, still a little bigger, but well, security is also very competitive there. SMOG, you see the timings for key generation are maybe a little slower at each security level, but it's a little smaller. I mean, it's a little more to the right, but a little farther down. And then some older Entru variants have the key generation time being much bigger, so they're more to the right. The sizes, well, you can see how the sizes compare. And then McLeese, well, the key generation is much slower, and the sizes for the key much bigger. On the other hand, if you look at the encapsulation, then, well, for McLeese, which again, Paloma's not in here, but McLeese and Paloma should have similar performance characteristics. You can see that McLeese, the encapsulation time is good, and the ciphertexts are small, so it's very far down in this graph. And then for Entru plus, you can see that the speeds are definitely better than for Kyber. And this is even after Entru plus, so this is including the recent changes to use Shake rather than AES and SHA-256 or SHA-12. And those changes generally made Entru plus slower, but even with that slowdown, it's still faster than Kyber. SMOG, you see, is also some good speeds for encapsulation, and the sizes are better than for Kyber. And then, yeah, this is something else which the dots change a bit depending on whether you're looking at an Intel processor or AMD. And then for, I'll finish with this graph for decapsulation. And this one you can see, for instance, looking at Entru plus 768 in blue on the left, that is faster for decapsulation than Kyber 90 768, even though it's using slower symmetric primitives, and significantly faster than Kyber 768. SMOG, you can see on the right there with like SMOG T5, it's not as good for the speeds, but still the sizes are better. So again, like I said before, don't just look at the timings, because in your application, the sizes can also be more important. And then down bottom right, the decapsulation for McLeese, which again, you can think of as a predictor for Paloma, that is something which is smaller ciphertext, but not quite as fast for lattice as lattices for decapsulation. All right, so those were all the graphs that I wanted to show, and I guess that's it for our talk. So thanks for your attention.